x equal to, you correct me if I'm wrong, ax squared, and this is from x is at 0 to 2, is that right?
Yes.
And then it was equal to just ax, this is from 2 greater than x less than 3, and it was 0 else. Everybody with me on this one, class? Now, the first thing you have to do for a density function, if you're going to calculate that constant, is realize that the probability density function integrated over the range of values that are possible has to be 1. That's it. There's nothing tricky about that. It will always be that. So I know that in this case, 1 would be equal to the integral, and I'm going to go from 0 to 2 of ax squared dx plus, and it's going to be the integral from 2 to 3 of ax dx. Now I'm just putting down the formula. This is, and again, this should be just about a gimme for everybody, a slam dunk, at least in my mind. Everybody with me on this? This is simple integration. Okay, so I have 1. The first one, I get 8x cubed over 3 from 0 to 2. Or it's a, and it would be 2 cubed over 3, plus, and then for this one, it's going to be a, and it's x squared over 2, or divide by 2, and then I have 3 squared minus 2 squared. I'm trying to be as clear as I can about this. Y'all with me? This was supposed to be just right down the line like this. So to solve for a, the only thing I have to do is break out all this stuff, and I get 1 equals 8/3 here. And then I get plus, and this is going to be 9 minus 4 over 2. And it would be a, so I invert that, and is a 36, or is it 6 over 31? I forgot exactly. Something like that. That was the only thing, it just straight through. The next part was, is that the mean value?
Yeah.
Now you can do it a couple different ways. You could do it with that integral of 1 minus the capital F of x of t and do the integral, but you don't need to do that. This is an extremely simple problem. So if you look at this, if I want the mean value of x, or the expected value of x here, it would be simply the integral from 0 to 2 of a, well really it's going to be x times ax squared, or if you look at this, it's going to be a x cubed dx plus, and then the integral from 2 to 3 of a x squared dx. Now does everybody follow me on this one? Just meant to be a straightforward, simple integration. Everybody? If you do this, well, yeah, you can say it's going to be a, and it's going to be x to the 4th over 4, or a over 4, and here you're going to have 2 to the 4th, plus, and then you're going to have a, integral of x squared dx will be over 3, and then you get 3 cubed minus 2 cubed. And a is 6/31, and when you put them, I just do the math on this one is substituted. What is the value?
2.
Yeah, it was, there's probably more clever ways to do this, but this works every time. And it's just, you know, just straightforward. There's no tricks here. Just multiply by x, that's it, and integrate. Nothing tricky at all. And finally, I think it's, isn't it x squared? Right, I want the expected value of x squared or x squared mean, correct class?
No, it's just the probability from 2 to 3.
Are we almost, can everybody do that one? You understand the only difference here is instead of multiplying by x, you multiply by x squared up there and do the integration? Everybody follow me on this? And then while I'm at it, if we got x squared and we wanted the actual variance, how would you get it? Just for completeness. If I want the variance of x which is equal to sigma squared of x, what would it be? If we had this.
That minus x bar squared.
Right, it's gonna be x squared bar minus x bar squared. It's important to remember these things. Make sure you know this like the back of your hand. This is like F equal ma or V equals I times R kind of stuff. And later on in your senior level courses, and even in communications, you're gonna see that it is assumed you know how to do this effortlessly, basically. This is not, it's not like taking a course in, you know, Mayan history where you don't need to know it after you take it. This stuff, this is how you make your money understanding this, so it's real important. Okay, well, I didn't ask this, so the probability of what?
From 2 to 3 of x.
All right, x greater than 2, less than 3, and I'm not putting less than or equal to just because there's no impulses. You don't need to get that formal. Y'all with me? That's just a simple integral, right? And it would be the integration from 2 to 3 of simply that f of x. And in this case, it's going to be a x dx from 2 to 3, or it's simply a times, or a over 2, and it's going to be 3 cubed, or 3 squared, pardon me, 3 squared minus 2 squared. And I don't know what that is, but can you tell me? It's like 0.4 something, isn't it? You have it, don't you? Or
It's 0.48.
anything else in that one? It was meant, honestly, I promise you, when I made this quiz up, it was meant to be a trivial quiz. I give you my word. I did not try to make this in any way, shape, or form tricky, but you have to have a very good understanding of how to do these kind of classes, this class of problems. And where it gets really, I'd say, complicated is when you have a density function that's going to be bimodal, something like this, where you're going to, it can't go negative, but where you get 2 peaks or 2 areas where it's doing this, then you got to be a little more careful with the integrations. Y'all with me, class? Any questions about that one? If you made mistakes, learn from them, move on, and whatever the reason is that you can identify as why you may have not done well, try to correct it, whatever it may be. And I can't, I don't know what all the reasons are. I've had all sorts of things told to me about problem students. All right, next. Now, I put up some PowerPoint slides from Dr. Denny, Tom Denny, and I think I looked at those and they're excellent to bring out the points without a lot of added information that can confuse you. Did you all see these slides, class? I posted a few of them. Y'all with me on this? I mean, I don't know how you felt, but I thought they were excellent. They're right to the point, nothing tricky. And I wanted to, before I move on, I wanted to do a few problems, and I want to make absolutely sure you understand how to do them. And I'm going to say this. Problems like this class of problems occur in the real world. And boy, without getting too deep into it, in radar, I encounter some of this, but I don't encounter it in the same way, in the exact same form as this. But it does have to do with, you know, if you know the flight path of something, and you can describe it, say it's a straight line, a linear equation. And I know something about the probabilistic, they're called swirling target models of the RCS of that thing. I can write equations, without getting too complicated in this, where I can get the statistical probability or expected value of the radar cross-section versus position versus time. Now it's this is getting way out from what you probably can appreciate. But the essence of the problem is the same as some of these. So for this one, this is 2.3-4. I believe I've assigned that one, correct? Isn't that right?
Yeah.
This is again on OneNote. Y'all with me on this? And I posted the book. I think I even posted this problem, if I'm not mistaken, right? And it says basically you have an equation, y equals 3x minus 4. So now I got a linear equation, and you know there's going to be a density function given for this one. And he gives you f of x, and here it's equal to e to the minus 2 times magnitude of x, and this is for all x. So it's everywhere. Interesting kind of problem. And what he wants is f of y. He wants a few other things. Didn't how many tried this from? All right, now it's a good problem because there's one part in there where what's the probability of y being greater than x? That one you have to think about. That's the last part. But this is kind of straightforward. If you look at this, f of x, and I want f of y. So first, the first thing, I know that f of y, this is a linear problem, is going to be equal to f of x. Here we're going to substitute in right here a function of y for that, and then it's going to be divided by dy dx. First, does everybody agree with that? I'm just trying to make it clear, right? Do you remember me doing this? And the way Dr. Denny does it, and it's in the book, what they do is actually say that for if I want f of y, he's going to come out and he's going to, well, he's basically going to say that's the integral from minus infinity to, and then he'll have whatever the inverse function, or he'll have of x, but x will be a function of y, of f of x dx. And when you do this, I'm not going to do it this way, I'm going to explain something. What he's really saying is, if I come over here, and I take a look at x, and I know this would be my f of x. So if I take a look at the probability of x being from, say, minus a to a, would be the integral of that. What does that correspond for in y? Well, if x is minus a, y here would be 3 times minus a, or it's going to be basically minus 3a minus 4, right? So that would be the lower limit, and the upper limit would be 3a minus 4, and it would be a different range. Do y'all follow me on this? And that's what would go here, but you can do it if you actually take a look at the notes. He does a pretty good job showcasing this. I prefer to do it this way, the other way. So I'm going to come here. If you don't understand it completely, please take some time to look at this and really see what it's saying and then apply it to problems. And there's, I didn't look in Chan's book, but I'm sure he has an entire set of problems related to this. They'll be more complicated. They won't be this easy. Chan has a way of taking things to another level. And I mean, it's probably good, but it can be bad because it obscures the truth. So for this one, first of all, I need dy dx. And dy dx, in this case, no tricks implied, that's just going to be 3. Do you agree with that? Just look at that. Everybody? Right? The derivative of that. Now I have that. And then I need x in terms of y. So if I have this, I have y plus 4 over 3 would be equal to x. Do you agree, class? Now I can go ahead and say for this one, it's going to be equal to f. And I'm going to actually put down the function, so it's going to be e to the minus 2 times magnitude of y plus 4 over 3, and then it's divided by 3, and that would be my f of y of y. Do you all agree with that? By definition, correct, class? So then, if that's f, I don't remember the form he has. Does he have it like this in solutions? Or I'm pretty sure he has it in a form like this. And then what does he want?
He asked for the probability that y is negative.
Okay. So the probability of y being negative, a couple ways to do it. First of all, we have f of y, just listen to me. I can take that and integrate it from minus infinity to 0. Do you agree with that? that would be the probability it's negative. I can do one other thing though. And this is the nice thing about these problems. There's several ways to get at the same answer. If you look at this right here, for y negative, right? If you take a look at this, make that 0, right? You find out, here's what I'm doing. If I plot it over here. Let's try to figure out the best way to explain some of these things to you so you can see it, what's really going on. So this is x and this is y. And I have this equation when, well, pardon me. I have this equation when x is 0, y is minus 4. Follow me? So here, there's the intercept. The slope of that line is 3, so it does this. Y'all agree? And if you think about the probability that y is negative is really the probability that x is below that value. Do you agree with that, class? I mean, how many see this right here? It's going to be the same exact thing. Matter of fact, we could fashion the problem that way. Do you see it in back there? So I can do it this way. It seems maybe a little easier because that integration is a little easier. If you take a look at it, I want to make sure you see this. So how do I find this intercept? That's where y is 0, right? Where is y 0? X equal 4/3, is that right? Y'all with me? All right, so this point right here would be 4/3. So it's the probability is x is less than 4/3. This can be a little tricky. I want you to just watch this. So when I come over here, here's my f of x. Now, the key is that absolute value. With me? So if you go ahead and say, what I really want is the integral of f of x dx from minus infinity to, you can actually take 1 minus the integral from 4/3 to infinity to. You all with me, class? But I'm going to do it this way for a reason. So now I have from, what is it, 4/3, right? This would be the probability of y less than or equal to 0 because the two bounds on the density functions are the same, or the limits, right? Everybody see this? Okay, do it with me now. So here's what I'm going to do. I got to break this up into 2 parts or I'll get in trouble. I'm going to go integral from minus infinity to 0, and f of x here is e to the minus 2 magnitude of x. I'll tell you why I'm doing it this way in a second. Plus, and then it's the integral from 0 to 4/3 of e to the minus 2 magnitude of x dx. Now, does everybody agree with this before I keep on just beating it down? Right? I did it for a reason this way. This integration is interesting, right? Now, that's an absolute value there, right? But I'm in the negative range, so it really would be e to the 2x. Does everybody agree with that? Because x is it's negative from minus infinity to 0, correct, class? And it's an absolute value, that would make it correct. Do you all agree? It's positive. All right, when I integrate that, what do I get? Well, I get 1/2, right? And then I get e to the 2x evaluated from 0 or 1 minus e to the minus infinity, which is just 0, plus then I integrate there, right? And when I integrate that one right there, I can get rid of this absolute value because that's going to be strict positive from 0 to 4/3 of x. Do you see this, everyone? When I do this, now I get the 1 over minus 2, but I can switch the limits and I can have 1/2, and it would be e to the 0 or 1 minus e to the minus, and it would be 4/3 times 2 or minus 8/3. And that would be the correct value for the probability of y equals negative. Can you tell me what that is? I've done all these, but I just don't recall the answer. Maybe I do. I have it somewhere. I don't know what it is. I don't.
The answer is
0.965. Is that out of the book, or did you just calculate it?
That's out of the book, and I just calculated.
All right.
it. Specifically, well, yeah, that's the answer to the final problem.
No, I think. Oh, is that the last part?
No.
I didn't think so. Now what? You're right. Hang on.
I think it's where it's finding the probability that y is, or it says y is greater than x or something like that.
Y greater than
Is that
x.
what it was?
Yeah, that's it. So this is the thing on words. So look at this graph. Right here. The probability of y greater than x, right? If you think about it, all these values down here are negative, right? For y. So it's never greater until you get in here, but still not, right? What do you have to go to? When y equals x, right? And if you do that, if you take a look at this, I'm using this equation right here. If I have y equal x, what that means is x equals 3x minus 4. I'm just doing the obvious, correct, class? Now I get minus 2x equals minus 4, or x equals 2, correct? At that point, any values of x greater than that, y would be greater than x. Do you agree, first of all? It's the wording that can get you. Do y'all, how many see this right here? Gotta make
Sorry,
sure.
why did you do the y equals x? And then
Well, remember, what we want to know is the transitional point. We know at this point y is 0 and x is positive, right? Y is not greater than x. When is y going to be equal to x? Well, make y x, set it equal to, follow me? So here's what I did. I just took y here, set it equal to x. Now I have x equals 3x minus 4. That's the point I need to know. Anything greater than that value of x, y is greater than x, because the slope of the line. Everybody agree with that? How many do? Are you with me? I'm trying to be clear. So now I know at that point it's 2, so how do you get the probability that x is greater than 2? The only thing I have to do for this one, I'm not sure how he does it in the book. You could take 1 minus the probability. It's less than 2, but I'm going to just say probability of x greater than 2 is just equal to the integral from 2 to infinity. In this case, it's going to be e to the minus 2x, because x is strict positive, dx, and that's going to be equal to 1/2. And then you could put minus in front of there if you wanted, e to the minus 2x evaluated from 2 to infinity, right? But I switched the limits, and then what that means is I have e to the minus 2 times 2, or e to the minus 4, and it's going to be minus 0, so what is that? E to the minus 4 over 2. This is small. I forgot the value. Anybody?
0.0092.
I think that's. Are you with me, class? How many students today? Now, that kind of problem I'd expect you to be able to do fairly easily and fairly straightforward. And if you're having concerns about these kind of problems, do all the problems that are assigned up. You have the solutions. I mean, all the problems. You don't have to just do the homework, but do them all. And I want to tell you one other thing about these. This stuff can get, and it will later, get very confusing. And that's the reason I'm encouraging you to now make sure you understand the simple stuff. Because some of the stuff coming up, I don't know if you've talked to other people who've taken random and Bashir and stuff, it can get extremely confusing. And I'm trying to make absolutely certain that the fundamentals you have down. It really will drive you nuts if you don't. Okay. And you have to be able to interpret equations. All right. Now, I want to get through Gaussian today, but I want to do a few other things because I think some of these problems are so good in terms of showing you what can be asked that is unexpected. Next. Oh, I forgot which problem this is. So I'm going to ask something. That's the homework problems I assigned refer to prior problems that I posted. And so for 2-4.1, did anybody have any trouble with that? Did you look at it? How many looked at it? Yeah, no problems? No problems? Okay. Because it's just asking, you have to get the density function for problem 2-3.2. And then find the mean value, the mean squared value, and you know, these are straightforward operations. Multiply by x, multiply by x squared, do the integrations. And the variance is just going to be the mean squared value minus the mean value squared. Now, I didn't talk a lot about this, but there are things called central moments that I'm going to bring up now. And don't ever worry too much about this, but when they talk about a central moment, here's what they mean. You have always, you're going to have an expected value of the random variable that we like to call x bar. That's typical. It's just the mean value, whatever it is. When you talk about a central moment, it's always going to take the random variable x, and then it will subtract from it the mean value, and it will be to a power n. Now, do y'all follow me on this? If you, and then it would be the moment of this, sorry, so have that over the top because of the average value. So when you talk about a central moment, well, there is no, if you think about the first central moment, let me get to this so you'll see. If we're talking about central moments, x minus x bar, it's always about the mean to the nth power, but the bar over here means mean. So it's an integral technically from minus infinity to infinity of this. So it's going to be random variable x minus mean value, constant, to n f of x dx. Y'all with me? Now let me go through this. N's an integer value. So the first central moment will be when n equal 1. Now, you can take one look at this and you know what the answer is. Just listen. It's a central moment, right? I take the random variable minus the mean value and to the 1 power, right? So I'm taking x, f of x dx and integrating it, minus x bar, that's the mean, times the integral of f of x, from minus infinity to infinity. Do y'all follow me? Well, that is the definition of the mean. So it's the mean minus the mean is 0. Can everybody see that? How many can? If you can't, just think about this. I'll break it up one time for you. So this is really the integral from minus infinity to infinity of x for the first central moment. Here, I'll say n equal 1 for this one. And it's going to be f of x dx. That's this one times this, and then it's minus, well, x bar is a constant, x bar times f of x dx from minus infinity to infinity. This is the mean, that is 1, so by definition it's 0. Everybody with me? All right, now, if you take a look at the second central moment, what that is, when n equal 2, I'll just put it here, when n equals 2, that would be the variance of x. Or really, it would be this minus the mean value squared. By definition, if you take a look at that. Do y'all follow me, class? Now, here's the important ones. Remember, these are central moments. The third central moment, when n equals 3, this is important. If you look at this, n equals 3. Well, when we get to Gaussian, you'll see this. Almost always the third central moment will be 0. The reason is this right here is going to be an odd function about the mean. See how you're subtracting the mean off of it? For a third central moment, that will be an odd function, and this will be an even, and you're integrating an odd from minus infinity to plus infinity, and it will be 0. Now I'm going to get to this more with the Gaussian distributions. Have you all heard of Gaussian? I think everybody's heard of it. But I just have to show you, this is what central moments mean. And if they talk about the third central moment, the only thing is, it would be that third power, or this would be 3. And that was asked in that problem. Did you all see that? Or not? If you look at it, this is, I think, 4.2, but he asks for the third central moment, and he refers back to problem 2-2.4. And in 2-2.4, it's basically the one where they gave it as a sine, or as a cosine for the cumulative density function, but it should have been a sine. And when you take a derivative, you get a cosine, but I will forego that one. Just remember that that's what that means. You're always taking any moment, central moment, you're taking the random variable, and you're subtracting the mean, you're taking that quantity to a power n. And if it's an even, it would be like 2, 4, 6, 8, and stuff like this. If it's odd, 1, 3, 5, 7. Now, there's one problem, last problem I'm going to do before I get out of here, and this is a little tricky. I don't think did I assign 2-4.4? No. No. This is a good one, but it'll drive you a little nuts, which is normal for these kind of problems. All right, so for this problem, what he's saying is that he has 5 loads that consume 10 watts when they're on. I'll just try to draw it here. They're independent, so we have 5 loads. They're all the same, by the way. And when they're on, they all consume 10 watts. So all these things consume 10 watts when on, and all of them have a probability of being on of 1/4. So 75% of the time, they're not on. You all follow me, class? So what he wants is, what is the mean value of the power? And I'm going to explain something. Remember, they're independent. One doesn't depend on the other. It's just like rolling die 5 times. And one roll doesn't have anything to do with the next one. So first of all, if I call xi, you might say the value of the power at any point in time. If I want them, y'all with me on this? I'm trying to phrase this in a way that makes sense. So the value of, and I is just the indices, so this would be like 1, 2, 3, 4, and 5. If I take a look at the expected value of just one of them, I'll call it xi. The expected value of the power of the first load, forget all the other loads, right? Well, if it's on a quarter of the time, and when it's on, it's 10 watts, I think we all see that. What would the expected value be?
2.5.
Just, yeah, 10/4. Do you agree with that? Or 2.5 watts. And you can call that xi bar. This one is a little tricky. All right, now, for just one of them, remember they're independent, what is the expected value of xi squared? Well, you think x is power, right? So if you take the power squared, it would be 100. Do you agree with that? 10 squared would be 100. I'll leave it as 10 squared. 10 squared. And then it's the probability of that happening. Y'all follow me? And what would that be? 1/4. Do you agree with this? Okay, and what is that? That's 25, isn't it? So I got the mean value, and I got the mean squared value just for one of them. I know this is maybe a little unsatisfying because it doesn't seem to have enough complexity in just this calculation, but you'll see how it works. So then if I want the actual, let me call this x squared I bar. Now if I want the variance of xi, just one of them, that would be the mean squared value minus the mean value squared, or it would be 25 minus 2.5. Does everybody agree with that?
It's minus 2.5 squared.
2.5 squared, I'm sorry, you're right. 2.5 squared. And I don't know what that is, but
18.75.
okay. Keep that number. Now, all these are independent. There's a couple. And this is something that's good about this. So, first, the average value for all of them. In other words, what is the expected power? If you have a power supply here, he's calling this, if you read this problem, it's kind of interesting. He has a power supply right here, and P max can only supply 40 watts. This is, so what is the expected value of the power supplied to those 5 loads? And your gut is right on this one. The expected value of the power supplied, I'll call it expected value of the power, and I'm just going to call that P bar. This is supplied to all of them. It would just be equal to the summation from I equals 1 to 5 of the expected value of the power to each one. Now they're all the same. You all follow me? And because of that, you can just say it's equal to 5 right here times 2.5. And that would be it. As a matter of fact, probably the most obvious way is just add them up, add all the powers, which should be 50, right? And then multiply by the probability, and you get the value, but that would be the expected value of the power. You all with me? You can call it P bar. And then the expected value of P squared on this one. This is the one I wish I could do a better job of explaining. Because they're independent in every sense, that's going to be equal to simply the summation of the squared value. Well, actually, they don't want that. They want the variance, the total variance of all the values of the power, or that's really equal to x squared bar. It's, let me just write this down. This is going to, I'll get out of your way in a second. Summation from I equals 1 to 5 of, and here it's going to be 18.75, because it's the same in all of them, summed, or times, it's really just going to be times that, and these are, I better do it this way, that makes sense to me. So it's really the variance of xi, sum from I equals 1 to 5, or it's 5 times that 18.75. Y'all with me? And we can get that. Now I'm going to say one other thing about this, because this one, it's hard to see this part. Let me get to the last part of this problem, then I'll show you one thing here that will help you, I think. I'll try to at least. It says, if the power supply has a maximum value of 40 watts that it can supply, what is the probability it will overload? I want you to all think about that for a second. So the max value is 40 watts, and they want to know the probability that will exceed 40 watts. Now this is a discrete problem. So you can have 10 watts, and if two of them are both going, 20, 3, 30, 440, 550. The only one that exceeds it is when all 5 are going. Y'all follow me? So if you were to do this, think of binomial, or that distribution. If we take a look at the probability that the power is equal to 50 watts that's being supplied by PRB, what that really is going to be, and I'll put the binomial up here, would be the summation n factorial, k factorial, n minus k factorial, p to the power k, and here it's 1 minus p to the n minus k. Now that's the probability distribution that we've talked about before, right? Binomial. Here, they want the probability of all of them on, right? So here, what we want is the probability of n equal k. Follow me on this. All of them would have to be on. You agree with this, class? So that's the summation from I, or from k. Oh, sorry. You don't even have a sum here. This is just a single event. So this would be equal to n factorial, 5 factorial, over k factorial, 5 factorial, 0 factorial. Then it's the probability of 1/4 to the 5th power. And then, well, see, n and k are the same thing, so anything to the 0 is just 1. And that really is going to be 1/4 to the 5th. Can you give that to me?
0.001.
There's probably a few more numbers after that, but it's what? It's about 1,000th, right? It's about 1 in 1,000 that it exceeds that for this one. That's an interesting problem. I want you to think about it. Now, back to this problem the way I would, or a lot of you can think about it. Think about if we wanted the mean squared value or the average value. Normally, what do you see if it's continuous? You see something where you have x and you have f of x, right? F of x is the probability density function, correct, class? Or, if you think about this, this x would be equated to the number of, or it would be, yeah, it would be discrete in this case, but it would be proportional to the number of power supplies on. Do you follow me on this one? Now, if it's just one, I mean, each one of these are independent, so what you have to do is get the probability from the binomial right here of one being on. Do y'all follow me? Just one. Then the probability of two being on. Then the probability of three being on. Probability 4 and 5, right? It's actually discrete, but you would get something like this. You would get a value, if this is probability of I, and that I is the ones on, and this would be I equals 0, 1, 2, 3, 4, and 5. And you would get something like this. Can you all follow me? That would be, and there would be low too. I mean, this is going to be, I think, maybe, I think it is 1/2, but I'm not actually sure. Now, if you wanted the mean squared value, you would take the probability of none being on times 0, because that's would be the power, right? Plus the probability of 1 squared, or 1 being on, times, it's the mean squared value of one of those, which would be 100. Follow me? Whatever this is, plus, then it would be 2 squared times the mean squared value, which is 100, right? Whatever the probability is, and you would do that. That's a more difficult way of doing that problem. Y'all follow me? It's much more difficult. If you don't see every intricacy of this, realize this is the normal way we did it. If we had x here and this is f of x, we'd square this value and integrate it over that range to get the actual mean squared value. Follow me? In this case, if we try to do it discretely, it would be a pain in the butt. I mean, I tried, you can do it this way, and this makes it makes more sense. But because they're independent, if you just find the variance of one, remember, they're all identical, right? So because of that, you can take the variance of just one of those being on, and you can add them up because they're independent. That's one reason. Now remember, some of this stuff gets into an area of dependency and independent, but the easy way to think about this, if they're discrete values, all events are independent, then if you find the mean value of 1, you can add it to the mean value to second, third, fourth, fifth, if they're independent. And same with mean squared value, only if they're independent. I wanted to make that point. You may not see everything that this problem really implies, but it's important, at least I say it explicitly right now. All right, now we're going to talk about the Gaussian random variable, unless there are any questions. And I want to tell you this is very, very important. Of the distributions, this and Rayleigh are the most important. So the Gaussian distribution has to do with the probability density functions that occur in nature. And then there's all sorts of mathematical theorems, and there's physics that prove this. The math on it gets a little probably difficult to appreciate, but and when we have a Gaussian distribution in Chan, I'm sure he has some chapters on that. I can tell you, maybe I'll give you some reading to get a better appreciation. Try to have an appreciation for why it's important. But when we talk about Gaussian, by the way, I assume it's named after Gauss. Do you know who Gauss is? He's probably the most famous mathematician frankly, ever, in my opinion. Gauss is a guy who is this brilliant, phenomenally brilliant European, and he was my hero when I was younger. This story might help you get interested in this. So I was in 2nd or 3rd grade, and when I was young, what teachers would do was assign something. If they wanted a grade, they would keep you busy for like 15 minutes, 20 minutes, just keep you out of mischief, and you had to hand it in. And they had to be something where the answer was obvious to the person giving it, but very unobvious to students. So Gauss was in this class. You gotta read this whole story, it's great. And the lady, the teacher, or the man, whoever it was, asked everybody to add the numbers from 0 to 100 up. And that was their, I don't know what you say, maybe their quiz or something. And so, the lady gave it to him, and Gauss came up about a minute or two later, just handed the paper. Teacher looked, that's right. Looked at Gauss and said, how did you do it? Do you know the story at all? Anybody? Do you know how he did it? Gauss was smart. He took and he wrote all the numbers. Then he wrote them backwards. All the way down there. And he added the columns. You could see this instantly. And there's 100. There's 100. There's 100. And there's 100. And there's 101 100s. Y'all follow me? It started at 0, goes to 100, so there's 101. And each of these adds up to 100. So he said, well, here's 100. Here's 1. He's going to be 101. But there's twice as many there. So you divide by 2. And it was the right answer. This is a 2nd or 3rd grader that saw that in a heartbeat. Gauss saw many, many other things. If you ever read about his life, he's brilliant. This theorem, I believe, statistical variation is something that Gauss is credited with. But he did a whole lot more things. I gotta tell you, if you actually look at the truly brilliant people in physics and math and things like this, over the last 600-700 years, not back in ancient Greek times with Pythagoras and stuff, but there were different concepts that were of interest, like right triangles. Gauss was one of them. Sir Isaac Newton. Do you realize he was credited with calculus along with a German, I think Leibowitz or something, was a German guy about the same time. There were so many incredible mathematical and physics finds in really about 400 or 500 years ago up to about 100 years ago, a little over that. And then the modern era of physics, and that was with Einstein, Enrico Fermi, all these other people came through. And Einstein's relativity changed the face of everything in physics. But all that stuff, they're very unique individuals, and they only come along about once every 100 years, one of them comes along, roughly. And it is amazing, if you actually look at this, what these guys saw compared to the rest of, I guess I won't say their colleagues, or their peers, but there's nobody like Gauss in math at that time. And there was, Newton just, how he came up with integral calculus, found the mass of the moon, or you should say the volume of the moon, all that, was phenomenal. Anyway, something to get back to some interest in Gaussian distribution. So by the way, this is statistically developed and proven. It is not something that's an observation like, you know what Maxwell's equations are? Right, Maxwell's equations are 2 curl equations that came about by observation. They're not based on like Moses came down off the mountain and gave you these laws. They're not. This one's pure math. It has nothing to do with physics in the direct sense, but it works because of the nature of things and the statistical processes, as far as I know it. So, what is the Gaussian distribution? Well, it says this. The density function is going to be equal to 1 over, and it's going to be the square root of 2 pi, and then it's going to be sigma of x, that's going to be the variance, or the standard deviation, I better put that down. Sigma of x is called the standard deviation. then it's gonna be times exp to the minus, and here you gotta be careful, it's x minus x bar squared over 2 sigma x squared. So that's the density function. Now, if you wanted the cumulative distribution function related to that, it would be the integral from minus infinity, and I'll call that x of, here, it's that 1 over the square root of 2 pi sigma x exp to the minus quantity x minus x bar squared over 2 sigma x squared dx. And technically what I should do is probably prime that right there, and prime that. But that is untractable. It doesn't have a closed form solution. So you need tables. Now your calculators can do this. Be thankful that we're going to do that too in a bit. Are you with me on this one, class? So I think the next thing I should do, I just want you to know that what we're going to do is be using this, and there are many, many things associated with this. When you look at this distribution, by the way, there's something that you'll see about the mean value. It's symmetric. If you look at this right here, and I'm going to say x bar is right here. That's the mean value. The mean value, it'd be a maximum. Now just look at this. You see how e, if I have x is equal to x bar, it's e to the 0, that's 1. Y'all follow me? That's the largest possible value. And that means out here, this coefficient will be 1 over the square root of 2 pi over sigma x. And it will do this. It's called a bell curve. Probably because it looks like a bell. Something like that. And you've seen these things, right? And then they talk about standard deviation. I'm going to put up a PowerPoint only because it's easier to see this way. And they're going to say this is one standard deviation this way and one standard deviation this way. And it's about 69% of the entire area is within one standard deviation. If you go out 2 standard deviations, it doesn't mean that total width is 2 standard deviations. It means from the mean value to the extreme upper or lower, it's equal to 2 standard deviations. You get 95%. 3 standard deviations, 99. I think I said something wrong about this earlier, in not today's class, but in an earlier class. But I want to do this because I can get to the point a lot quicker, and I can show you this. My drawing isn't very good. So I want to try to do this. And believe me, I hate PowerPoints more than you do. There's a little thing here somewhere. Let me just start that screen, I believe. I almost never use this. In this case, I'm doing it because it showcases it perfectly. I hope this is. lights off, I would, but I think we'll be all right with this one. Just please pay attention. And these slides are up. As soon as it comes up. If it comes up, wait a second. It comes on. Nothing. Plugged in. Can you see a power cord in there? There's that.
Connected up under,
Huh?
it's connected in like inside of here.
It's what?
Looks like it's connected inside of here.
It's not, I mean, there should be, it should be plugged into the wall. Is there a cord there? You see?
I don't think it's plugged in. I don't know what that cord is.
This cord right here is just, this is just, I don't think there's any power right there. And there isn't power here either.
Like I see the power strip up under there. I just don't see my cord.
Where- I can't bend down with that hip. I'm not familiar with using this thing. Do you see anything in, hey, wait a second, wait, right here. What is this?
That's just the air. Maybe plugged in.
Pardon?
It's plugged in now.
Oh, there you go. Okay, thank you. Let's try this again. Is that on? Yeah. Just give me a minute. I want to just go through this, two things with you. Hopefully, thank you very much. here's the Gaussian, if you just give me 4 minutes of your time, I'm sorry about this, I didn't expect this. What he does is just show a picture of the Gaussian random variable or normal distribution. And he makes some notes. The model's a large number of physical random systems it does, easily extendable to a large number of random. And if you add up any two distributions, any two like x and y, where both have Gaussian, the resulting probability density function will be a Gaussian. Remember, this is all based on statistics that are beyond us right here. And you'll notice this right here, this is important. If you take a look at the probability of x being within 1 standard deviation, it's 68%. Within 2, 95. Within 3 standard deviations, 99.7%. What it really tells you is if, in fact, the event you're looking at falls in a Gaussian distribution, then this tells you how narrow, you might say, or how limited it is. It's important to at least have an appreciation for that. The next thing is central moments. Now, with Gaussian, I want you to listen to this. Gaussian random variables, all the odd moments are 0. So it would be odd moments here. Right? If you took x times f of x, the mean value is 0. If it's just think about that now. Well, I take it back. Let me say this different. Sorry. If you have n equals 1 or equals, because you're going to take x minus x bar, and if you think about a central moment, even though the mean value won't be 0, the central moment will be. So when n is 1, 3, 5, 7, it's 0. However, if n is even, I can't prove this, but if n is even, then the value of a central moment is just the odd values, 1, 3, 5, and then it's really going to be 1 less than the actual place you stop at. So if the 6th central moment would be 5 here, oops, sorry. And it just equals that sigma to the n power. Now sigma is going to be the standard, is going to be the standard deviation. And then of course for n, or the mean value, the mean squared value is not a simple formula. Here's the distribution I put up integrated, so this is the cumulative distribution function. I think you remember me putting this thing up here a second? I was just telling you that's the obvious fact. Now, this is important. The normalized Gaussian distribution is this. We're going to take the actual, say if you have a mean value and you have a value of x and you want the probability of x being less than the event, you have a standard deviation. If you calculate this, x minus x bar over sigma, you can go and look it up in a table, and he has this symbol used for the table, and that's capital phi, I believe, in Greek. Anybody here in fraternities? Well, I believe, or sororities, I think it's the Greek letter phi, capital phi. And you're going to see how this works in a bit, but this is real important what I'm about to tell you. And Tom Denny put this down here, that this is sigma, not sigma squared. It's real important to note that because people do make mistakes. Now, I'm going to level with you guys. I don't have time today to show this. You don't need to use these tables. Your calculators. And next time when I start, I'm going to have everybody get their calculators out and make sure you know how to use them to calculate these things. Now, this is my own personal peeve. I do not like looking up things in tables if I can just punch in numbers to a calculator and get them. I despise it. Did you have to do steam tables in thermo yet? I hated those. I despise those. I hate interpolating. You don't have to do that. We're in a modern era. Your calculators provide that information. And I assume everybody has a modern calculator. I mean, any of the modern TI ones, 84, 83, 89, is there a 93? What's the other one? Inspiring, all those things. I gotta tell you, I'm gonna be doing this stuff. We're gonna be talking about Gaussian distributions. I'm going to give you some problems. I'm going to ask you just do the, I didn't have enough time to get through this today, do the reading, and next time, and I'll give you some homework, whether you can understand it or not, but see if you can figure out in your calculators how to do this. your statistical packages, I think, are called normal distribution function, or something like that. If you look it up on the internet, they'll show you how to use it to do these problems. And honestly, because Gaussian is used by so many people, I mean, Gaussian distributions, they describe everything just about. I mean, if you think about the velocities, you know, there's basically here, we have air molecules bouncing around. The temperature is related to the entire energy, average energy of certain volume. Well, the velocity x, y, and z of those molecules is distributed in a Gaussian way, right, with a mean value. And we'll see how all this stuff describes nature as well as probably some non-natural processes in the grand scheme of things. But we'll get to them, and thank you.